Hi Kin 250. I hope y'all are having a really good snow day. I hope you're not too upset with me for making us do an online lecture anyway. I just don't want us to get too far behind, but I promise you this will go much more smoothly or just a lot quicker than a normal classroom period. We were originally scheduled to do a lab today, or part of a lab, but I'm going to push all of that to next Tuesday. So make sure you come to class on Tuesday so you can finish the whole lab. So today we're talking about correlation and regression, and I'm sure many of you are actually pretty familiar with correlation right off the bat. And since this is a recorded lecture, I'm going to kind of click between a few screens, but I believe you do all have the links that I'm going to share with you. There's going to be a one period in here where I play a TED Talk, and if you want to skip over that for the sake of time, go ahead. But if you want to sit there and listen, then you should. It's a really interesting talk. But just to give you a really quick understanding of what correlation is, because that's really what we're talking about today. Correlation is really the relationship between two variables. So just real quick, want to show you this kind of funny thing. I'm sure many of you have heard some funny correlations in your life, but here's this website that correlates a couple. Just every day they come up with a strange correlation between two variables. Okay, so some of them are pretty depressing, which is not by choice on my part, but you can see that a lot of these things just correlate really, really well with each other, and we determine that based on this value we see right down here. But they don't really make much sense. Like we can see here that this is almost a perfect correlation, and the two things that are relating to each other is divorce rate and margarine, as in like butter. Why would those two things relate at all? But apparently they correlate very, very well. Okay, so really that's all we're looking at is correlation, and we'll talk about why we can't really make too much sense of this value and this correlation towards the end of the lecture. Just moving forward, okay. We have a few learning objectives. Your book outlines a few extra things, but these are the things I want us to focus on for the class. Like you'll see that there are a couple other types of correlations that you can study, but these are the ones that we're sticking with. The Pearson's R. And just as a reminder, we talked about different types of statistics. So remember that there are descriptive statistics, and then there are inferential statistics. Now, if we're in class, I'd ask you to help me understand what descriptive statistics were and what we can do with them and the limit of descriptive statistics to kind of segue into what inferential statistics are. So what we're doing here in today's lecture is kind of starting to trickle into that inferential statistics area of this course. Okay, so it's a little bit more complex, but we're going to have to use some of the knowledge that we have in the past to understand our inferential statistics. Okay. So bivariate correlation is what we're focusing on, and like I mentioned at the very, very outset of this lecture, that it's a linear relationship between two variables. So the key thing here is that they have to be continuous variables, and this is where understanding the level of measurement is really important. So we know that we can't really, correlate nominal variables, right? So a continuous variable means there's just a breadth of responses, numerical responses that could be for these different variables. Okay, so we're going to talk about a few things that help us understand correlations and help us interpret correlations. So like I said, we're going to focus primarily on Pearson R, but your book talks about Spearman-Rowe. Spearman-Rowe is about more of an ordinal correlation, but we're not going to worry about that because it's rarely used. So Pearson is what we're focusing on. Just skip that whole Spearman section in your text. The next thing we're going to figure out is the strength of the relationship, and there's a certain way that we interpret that, and then the direction, which is just a sign, and then the shape of the relationship. So remember that we're talking about something being a linear relationship, so that just essentially means a line. But I'll show you a slide that kind of helps us understand that idea of a shape of a relationship. Okay, so Pearson's R, like I mentioned, is what we're focusing on. So I already said that we can't really use nominal data, can't really use ordinal data for correlations, but we can use ratio and interval data. So remember those levels of measurement. We can only use ratio or interval variables. Okay. So as we figure out what our correlation is. And often this is done using a computer, but because I'm so mean, I'm going to make you do it by hand. But once you figure out what your actual correlation value is, then you can determine the strength. So correlations range from a value of -1 to a +1. So remember that, a -1 to a +1. So if you end up finding a correlation that exceeds that value, something went wrong. You need to go back and trace your steps and figure out where things went wrong. Okay, so it should only be from a -1 to a +1. So if we have a value of 1, an absolute value of 1, it's a perfect relationship. The two are perfectly related. Okay? Now you can see from this table that's here, those relationships, they have some ranges in their strength. So if we look at the very bottom of this table, it ranges from no relationship all the way up to the top, which is a strong relationship. So make note of the language that's used here. Remember, we're talking about strength. So it goes from no relationship to weak relationship to moderate, moderately strong to strong. You'll see in other fields, or depending on the area of research, that these will kind of vary in terms of the value you get and whether it's strong or weak relationship, etc. will depend. But in this class, this is the table and these are the values that we are going to use, which are pretty popular in many domains. These are the values we're going to use. So when you find your correlation value, remember this table and figure out what the strength is. Right? Okay, so now the next thing we need to consider is the direction. And like I said, you determine the direction just by whether there's a negative sign in front of the correlation value. And if there isn't, then it's a positive correlation. If it's a negative sign in front of that value, then it's a negative correlation. Okay? So what a positive correlation means, what a positive correlation means is that when one variable goes up, the second variable goes up. Or it can also mean when one variable goes down, then another variable goes down. So an example of a positive relationship that we're all probably pretty familiar with is something like if you eat more calories, if you have more caloric intake, higher caloric intake, likely your weight will go up. Okay? Now, that same relationship can be true for someone who's dieting, right? But it would still be a positive relationship, but we could see the variables going in the opposite direction. Now, if you reduce the number of calories that you're taking in, then your weight will also go down. So you see that the first example is where both go up, the second example is where they both go down. Now, a negative correlation is where one variable goes up and the second variable goes down. Okay? So one variable goes up and one variable goes down. So there's a negative relationship. Okay? Okay, so I talked about how I would identify, I'd give you some pictures that help you understand shape. So remember correlation, we're really concerned about a linear association or a linear relationship between two variables. But if you look at these photos that I have up here, you can see right smack in the middle there's a big circle. And you can also see by looking at that value underneath that box right here that the correlation is 0. So there is no relationship between the variables that we're trying to correlate here. So really what we're saying is nothing really relates, nothing really associates, the two are not linked. It's kind of a random association. That's what we would say about that. You can see for these two on the far extremes, here and here, you can see that those represent a positive, perfect correlation, whereas one goes up, one variable goes up, the other goes up. And the way that I know that is if these are our x and y axes, one variable will be labeled on this side and one variable will be labeled on this side. So if we look at our calorie and weight intake, let's say that calories are on the bottom, weight is on the line here. The more calories I take in, the higher my weight is going to be. And you can understand it that way. Okay? Now over here, this is a negative relationship. So as one thing goes up, the other value goes down. So when you look at something that's plotted on a chart, you can look at the general shape that you see in that plot, and you can determine if you think it's a positive or a negative relationship. Okay, so those examples in the top row show either no association or a random association, and then a perfect correlation on those extreme values. Okay, but what you see in the bottom two is they're not as strong of a relationship, but there still is a relationship. And just by looking at the plot, so just by looking at those values, those scattered dots all over, you can probably make a good decision as to whether it's a positive or negative. So if those lines weren't there, you'd probably still be able to understand that the one on the left is a positive relationship and the one on the right is a negative relationship. And I also realized the signs are there, so you probably could have just looked at that as well. Okay, now, one of the things we have to be very wary of when we talk about correlations is that we're not talking about one thing causing another. Okay, but often in our world, people talk about it in that way. The news puts things out there and people interpret it as X is causing Y, when really all that's being shown is how the two relate. Okay, so there's no proof at all that X is going to cause Y. So you have to be really careful about the wording that's used and the language that you use. Okay, so language like affect or influence, that is going to infer that there's some kind of change happening. So if I'm saying X will influence Y, then I'm kind of saying that there's causation. But if I'm just looking at a correlation, I'm just looking at the relationship, I have to use different language. And I'll give you some examples in a few slides. But the images that I have here are some classic examples of some correlations that people have kind of, misconstrued in a way. And the ice cream indicates the one that you all have probably heard, that ice cream sales and crime, both of them indicate this, but ice cream sales and crime correlate really highly with each other. So ice cream consumption and crime. So basically, people have often made the wrong inference about this and said that, the more ice cream that's being eaten, the more crime. But what we know is that really all that is just a relationship. So the more ice cream that's being sold and consumed is related to a higher frequency of crime as well. But we can also think that, oh gosh, there's probably something else that's going into play here that's affecting this relationship. Why are these two things related? And the answer is that the two things happen a lot more in the summer. So it's hot in the summer. And people, when they're hot and they have some free time and they're outside, they enjoy a nice ice cream cone. The other thing that happens when it's hot is that people get agitated, people get irritable, people get angry. And I'm being dramatic here, but this is the truth, is that more crime occurs in the summer for these reasons. So if the two things happen more in the summer, then they're likely going to be related. Okay? So now, if you want, this is the section where I'm going to play the TED Talk. It's about 5 minutes long. If you want to skip over, go for it. But this is just an example of how correlations do not infer causality, okay?
Welcome. I came here today to warn you about the dangers of ice cream. You may not be aware of this, but these innocent-looking cones full of sweetness are one of the major causes of drownings. And I've got the numbers to prove it. So if you plot a graph of the number of ice creams that are sold, and you compare it with the number of drownings, you can see there is clearly an upwards trend. And I think it's very safe to conclude from this that we should ban ice cream, because it's very dangerous. Since you are all smart people, you've probably figured out there's something wrong with my example. What's really happening here is, of course, that there is an underlying factor, which is nice weather, you might have guessed it. And if the weather is nice, more people will go out swimming and unfortunately drown. And at the same time, more people will buy ice cream. And it's not the ice cream that's causing the drownings. And here it's really easy to see that there is something wrong, but jumping to an incorrect conclusion about causality when you see a correlation is the most often made logical mistake. And today my goal is to make sure that in the future you can recognize this mistake, and I really hope you can avoid making it in the future for yourselves. And I'll do this by just giving some famous examples. And the first one is really rather innocent. The fact is that married men live longer than single men. If you look at the statistics, you see that this is really happening. And women's magazines, they like to conclude from this that marriage is very healthy for men because it makes them live longer. Well, a friend of mine, he likes to joke that marriage mainly makes life seem longer, but that's because his wife is... But so, can anyone guess what's going on here? Because there is a causal relation, but it's the other way around. The fact is that men who are healthy and rich and well educated and have a much higher life expectancy, these are the men that are much more likely to find a wife. That's the way women are. And the guys who have a very low life expectancy, so they're unhealthy and poor, they are not as likely to get married. So it's the high life expectancy that is causing the marriage, not the other way around. Well, and this, of course, it's not so serious. No one will get married just because he read this. So let's move on to a more serious example. It was also more serious research. In Nature was a study in 1999 that showed that young kids who sleep with the lights on, that they have a much higher probability of becoming short-sighted later in life. Well, and the researchers, they were smart and they wrote very careful that they had found a correlation, and they didn't know how the causal relation might work, but just to be sure they advised all parents to turn off the lights at night. And in the popular media, this became that bed lamps were night abuse, children's abuse, and that it was very bad if parents used lamps in the bedroom. And many parents were worried. I can imagine if this would have happened when my son was sleeping with the lights on, I would have felt really bad. But luckily, the article had to be corrected the next week. And maybe some of you can guess, if there are biologists in the audience, they know. Short-sightedness is genetic. And so it's parents who are short-sighted, and those are the parents who like to leave the light on in the bedroom. And they also are the parents who have short-sighted kids. So again, a simple mistake, easy to make. Then what is, I think, the worst example I know many of them. I see at least one of these in the newspapers every week. But this is a classic one. In the 70s, researchers found that there's a very strong link between kids who do well in school, get good grades, and kids who have a high self-esteem. And they concluded from this that it's very important to make sure that young kids are, raised to be confident and proud of themselves, because if their self-esteem is high, the good results will follow. And this was what was told to parents, especially in the US, for generations, that just make sure that your kid is proud and confident, then all will turn out well. And many years later, someone did another study just to see in which direction the cause was working, and they found that it was in the opposite direction. So the good grades were causing the self-esteem, and self-esteem wasn't causing good grades, and it was even worse. So kids who are raised just to have high self-confidence and not excel at anything, it can be sports or music, doesn't have to be school, but kids who are just proud of themselves and then fail at everything, in the end they will have a very low self-esteem and not be able to make anything of their life. So this was a very serious correlation mistake. And what I want for today is for you to remember that the next time someone wants to prove that there is a causal relation between something and something else, it can be anything. It can be vaccines and autism. It can be female bankers and the financial crisis. And if they point out to you that there is a very strong relation, remember that it's not enough to have a correlation. It gives a very good hint of what might be happening, but before you can conclude that one thing causes something else, you need to know why it does and how it does. So when in doubt, just remember the ice cream. Thank you very much.
Okay, so if you skipped that part, I would like you to watch it. She makes a really, really good point throughout that whole thing that I'll talk about later in class again. So just to give you a little bit more reinforcement about that language, so make sure that the language that you're using is the right kind of language. Okay, so like I said before, using words like affect and influence infer causality. And what I mean by infer causality is X is going to cause Y. Okay, so in this case, it's off-task behavior and academic achievement. So basically, it's how does off-task behavior affect academic achievement? Now, this is a fair question to ask, but if we're only looking at the relationship, this is not a good way to frame it. A better way to frame it would, if we're looking at the relationship, would be to use words like association or relationship between. Okay, so we're looking at correlations. You just ask the simple question of what is the association of students' off-task behavior and their academic achievement. And the example below also corrects the previous example. Okay. Now, correlations, like we said in the earlier parts of this lecture, assess linear relationships, but sometimes we can have curvilinear relationships, and what's going to come up when you do a correlation is that that's going to be a correlation of 0. But what you want to do is, if you're able, is to look at that scatter plot and see if there is some kind of relationship there. So you would still report a correlation of 0, but if you're looking at the visual representation here, you'd probably say, well, it looks like there's a curvilinear relationship between anxiety and performance. And what we mean by that is that your performance will be at its best when you have moderate amounts of anxiety. But when you have really low anxiety and really high anxiety, your performance is going to be low as well. Okay. So here's a correlation example. You all have these values in your table as well, but what we're looking at is the correlation between height and sit-ups. So essentially what we're asking is, how does someone's height relate to how many sit-ups they can do? So looking at this table, what we would want to do is just to plot this. So if we plotted it, this is what it would look like. So if you look at this, there's no line here, but if you just look at this, what direction do you think you're seeing here in the relationship? Is it positive? Is it negative? Or is there no association or a random association? What do you think? Okay, spoiler alert, it's a positive relationship. Okay, so you can see that if you were to draw a line through this, even though they don't fit really tightly to the line, it still is a positive relationship. And we're going to carry this example out in the following slides. So here's the formula for correlation. People, don't panic. Okay, don't panic. You actually know what all of these symbols mean, but if you need help, there's this key right down here at the bottom. So what you need, you all know what n is. N is your sample size, so how many people are in our sample. We know that sigma means the sum of, and that's going to help us understand all of these. So we're using x and y to indicate our variables. Okay, so height and sit-ups. So x and y, and you can figure it all out from there. So the sum of x and y times each other, the sum of just x, the sum of just y, and the sum of all the x's squared and the sum of all the y squared. If you have all that information, you can plug and chug and figure out what your r is going to be. And just as a reminder, r is the symbol for correlation. So here are the steps that you need to know to calculate your r, so to calculate your correlation, right? So these steps, I don't expect you to, looking at this slide, be able to write all these out, but what you will have to be able to do is to be able to do it properly within a table. So if you're able to complete a table like this, you're able to, the steps, okay? So let me go back one slide real quick, but basically what you want to do is create that table, if it's not given for you, and then square each x value, so height, and each y value, so sit-ups, and then place those in the columns down below, okay? And then you're going to basically sum all of the columns so that you have all your values down at the very bottom. So you can see that here, right down here at this bottom row, okay? So in an example that you would have everything in these first 3 columns, but you would have to solve for all the other remaining columns. So you can see here that height is our x and sit-ups are our y. Okay? So when I'm trying to figure out x squared, I'm taking this value here, squaring it, and putting it over here. Okay, then I'm going to go down here, find this value here, squaring it, and putting it in this column here. Be really careful where you place your values because you don't want to put it in the wrong column. Now then you need to do the same thing for your y. So you're going to take this value, square it, and put it over here, right? And do that all the way down for all of your values. Now what this column is right here is this value times this value, and it equals that. So you're going to do that all the way across the board. And then when you get to the bottom, you're going to add them all up in each column and get your values that you put in here. Right? Okay, so now that you have those values, you seriously just plug and chug away. So make sure it's all straightforward, you've got it all clear, you've done your math properly, and you put it in the right places. Now be very mindful of the brackets and the parentheses and remind yourself of the order of operation, so PEMDAS, right? So remind yourself of that and in what order you do your math. And then plug away, and then we will get, if we do this problem with height and sit-ups, we get a correlation of 0.61. Now, we know just by looking at that number that, like we suspected when we looked at the scatter plot, it's a positive relationship, right? There's no negative sign in front of that 0, so it's a positive relationship. The other thing we can tell is we can figure out the strength of that relationship. Now, if we go back to that table, we can tell that a correlation of 0.61 is a moderately strong relationship. So really what we're saying there, what we're saying there is that someone's height and sit-ups are related in that the taller someone is, the more sit-ups they do. Right? So the taller someone is, the more sit-ups they do. Right? Okay, so go back to your table to figure out the strength. And then the last thing we're going to end with here today is identifying our coefficient of determination. And once you've figured out your correlation coefficient, which is just your R, you can figure out your coefficient of determination. It's just R squared. Okay? So what R squared is, or what your coefficient of determination is, the value that basically tells you how much variance is explained by the other variable. So basically, how much does someone's height actually explain their sit-up ability? Okay, so if we do this for the previous example, we just take 0.61 and we square it, because 0.61 was our R. So look, putting it here, square it, we get 0.3721, and we want to report this as a percentage. Okay, so report it as a percentage. So what we can then say is that the percentage of sit-ups that's explained by height is 37.21%. So basically, the outcome of sit-ups, so how many sit-ups someone does, is explained by the differences in height in the class. Let's say it's a classroom. Or height accounts for 37.21% of the variation in sit-ups performed. Okay? What we can tell by that is that there's still something else out there that's also going to contribute to or influence the number of sit-ups that people do. In fact, there's other things out there that still explain 62.79% of the variance in sit-ups. Right? So we can talk about this again next class, but this is about it for today. Get some practice with those values. Revisit this chart to plug it in for yourself because I believe you did not have it. And good luck. Keep practicing those Z-scores. All right, we'll see y'all next week. Have a good snow day.